find it. And I'm very happy to introduce the next speaker, Agnese Bissi from ICTP, telling us about multiparticle states in CFTs.
Thank you very much. Thanks a lot, first of all, to the organizers that I happen to know all of them very well. So this conference is always very nice. I really like the Eurostring conference every year. So I'm very glad that this year happened here in this beautiful auditorium. And thanks a lot also for inviting me here to present my work. So what I'm going to discuss today is essentially how to deal with multi-particle states in conformal field theories, in particular in unequal force superior mills that I'm going to discuss a bit later. And we started this program a couple of years ago with Giulia Fardelli, who used to be my PhD student and now is a postdoc at BU, and with Andrea Manenti, who used to be a postdoc in Uppsala. So what I'm going to discuss is mostly based on these two papers, and I'm also going to discuss something that we are thinking about now. Okay, so what I'm going to present today is how to study correlators in unequal force superior mills. And we think about unequal force superior mills having a SUN gauge group. And I'm going to focus in the regime in which the Toft coupling lambda, which is G square n, large, so I'm going to consider the regime of what we usually say strong coupling, and I'm going to consider these correlators in a regime in which the rank of the gauge group is going to be taken large. I'm going to be very specific a bit later, but just to set up a bit what I'm going to discuss. This is actually the reason why we studied this kind of regime is because this is what is called holographic regime, meaning that we can also relate the correlators in our unequal force superior mills with amplitudes on ADS, and this I'm going to discuss later on. But the main aim and what I'm going to discuss today mostly is how essentially we can read off, I mean this I think all of you already know, the fact that if we study correlators, we can read off the spectrum of the theory. So specifically what I'm going to discuss today is how to extract from correlators in unequal 4 the spectrum of multi-trace operator in the theory. That's the goal, or at least that's what I prepare to discuss with you. So let me first start a bit by discussing the ADS-CFT dictionary, just because I want everybody to be on the same page. So as I said, I'm going to discuss four-dimensional unequal 4 superior mills with SU1 gauge group and an SU4 symmetry. This is going to be important later, so just remember that each time that we are going to see an R on my slides means that I'm talking about R symmetry. And this is dual to type 2B superstring theory in ADS-5 cross S5, as we heard already yesterday. So, as I mentioned before, the gauge group rank is N and the coupling constant is G mills. On the ADS side, we have the string length, which I denoted here a root of alpha prime, and the string coupling. So the relation between these two theories is made in this block here. So N, the rank of the gauge group, is proportional to the inverse of the string coupling, and lambda, which I already introduced before, like G square n, is alpha prime to the -2. So in particular, in this talk, I'm going to consider the leading order in this expansion lambda. So I'm going to consider only the first correction in this parameter here. So I'm just considering leading order there, so just supergravity regime. And instead, I'm going to consider expansion in N, so expansion in the inverse powers of the string coupling. Okay, so this is very important for what I'm going to present. So in particular, also, as we know from ADS-CFT, we know that we can consider correlators on the boundary here, so correlator on the conformal field theory side, are mapped into amplitude on the ADS side. So this is much more generic on what I'm going to discuss, but in particular, we know that the weakly coupled regime in the bulk is supergravity, and this essentially corresponds to this expansion that I already discussed. discussed, which is a large central charge or large n, because the central charge is proportional to n, and the string length to 0, which is what I said already. So in particular, if we consider 4-point correlators in a large n expansion on the conformal field theory side, this corresponds to loop amplitude in ADS for the same reason I said before. So we said that n is proportional to G strings, the inverse powers of G string. So we see that each time that we take a large n expansion on the CFT side, we are probing a loop expansion on ADS. So in particular, let me just introduce a few objects on the conformal field theory side, just to introduce a bit the notation. So here, let's consider the 4-point function of 4 identical operators. We know that due to conformal symmetry, this is fixed to be a function of only U and V, where U and V are the cross ratios which are defined in this way. And then there is this factor here, which depends on the dimension of this operator. Sometimes I refer to this operator as external operator, and this is the dimension now of my external operators. And yeah, this I already said. So another point is that we can expand this 4-point function in terms of conformal block, meaning that we can write down our 4-point function as a sum over the dimension and the spin of what I instead call intermediate operator that I denoted here. So this is a sum over all the possible primaries which appear in the operator product expansion of these two guys and these two guys. And these conformal blocks are completely fixed by conformal symmetry. And this A delta and L is nothing but the 3-point function between O and this operator, which has dimension delta and spin L. Okay, so the most important point that I wanted to stress here, because this is going to be slightly different in a few slides, is that this sum here is a sum over all the possible primaries which appear in this operator product expansion. So when I'm going to introduce supersymmetry, there will be a slight change here. Okay, so now what is the logic? The logic is that I'm going to take my 4-point function and I'm going to expand it in large n, as I said. So there will be a leading term, then there will be a sub-leading term that goes like 1 over n squared, then another term which goes like 1 over n to the 4, and so on and so forth. And if we think about that in the holographic context, the one that I introduced you before, and I'm going to discuss a bit later, so the G0 term is going to correspond to just a disconnected diagram here. Then at order G1, we are going to have this quartic term and this other term, which is just an exchange here. So this is again order 1 over n squared, while at order G squared, in principle, so that there is this this diagram here. There can also be bubbles, but in this the particular case of n equal 4, they are not appearing. But this is a kind of pictorial illustration relating how we can expand again our 4-point function in inverse power of n, and the fact that this corresponds again to the loop expansion. So here you see that there is the disconnected part. This is what I will talk and denote by the 3-level part. So the 1 over n squared is what I call 3-level, and then you see that here there is a loop, then there will be 2 loops, and so on and so forth. Okay, so this is why I'm referring to that as loop expansion. Okay, so let me just comment a bit on the spectrum of n equal 4. So most of you, I think, know what I'm saying here, but this is a bit a motivation that we had before starting this whole program. So we know that the spectrum of n equal 4 Super-Yang-Mills, I think it started actually here in Sweden, that using integrability methods, we know that the single trace sector of the spectrum is very well understood. So we, at any value of the coupling constant, essentially we know the dimension of single trace operators in n equal 4 Super-Yang-Mills. And so by now, I think we can reconstruct all, we have equations that is it possible to solve? And this gives rise again to the dimension of the full single trace sector. Now, if we go away, and again, this is mostly based on integrability methods, which essentially require our theory to be planar. So if we want to go a bit away from the planar limit, it's much more complicated. And in particular, for the multitrace sector of the spectrum, very little is known. So there is some information that one can infer from studying higher, like 4-point function using integrability method in the weak coupling regime. But other than that, very little is known about multitrace sector of unequal force invariant Mills. And the kind of question that I would like to address, or at least say something about, is how we can access this piece of information. So in this part of the talk, I'm going to essentially present two methods out of the three that I could think of. So the first one, again, remember that I'm going to work in this expansion that I said before, in the regime I was mentioning before. So one way to access this sector is to study large N expansion of single trace 4-point function. I will discuss much more in details what I mean by that in the following part of the talk. Then there is another way, is by studying, again, large N expansion of 4-point function of higher trace operator. What I mean by that is that instead of starting with the 4-point function of single trace operator, so where the external operator is single trace, we can start inputting some operators which are intrinsically higher trace, so that we will give access to the multitrace sector. Or there is another way that I'm not going to comment about it, but I wanted just to point out to, because maybe some of you work on that or they are more familiar with this, is that instead of studying 4-point functions, we can study higher point function of single trace operator. This is very similar to the point one, but I don't want to comment more about that. We can discuss over lunch if you want. But this is another way to access this multitrace sector. So what I mean by that is that essentially in this sum, that let me maybe go back a bit, that in this sum here, there will be both single trace, double trace, and all the higher possible trace operator. So I would like to essentially understand the sector that appear in this sum, which corresponds to higher trace operator. So what I mean in the previous slide is that if we study these correlators here, so for instance, this G1, we soon have, if we study by single trace operator, we soon have that this object contains a double trace operator. So this, I think, is what I have in my next slide. So scenario one, so the one that essentially involves the study of 4-point function of single trace operator. So let's try to understand it a bit. So this is a 4-point function, and again, if we study it in the large N expansion, as I said before, so in this disconnected part, so if we study the correlator and leading order in N, we see that as intermediate operator, we only have double trace operator. So in particular, the reason is that this 3-point function here is of order 1, so the full 4-point function is of order 1, so we just have the identity operator and these double trace operators. Again, in the limit I discussed before. Then, if we go to the 1 over n square case, again, we also have only double trace operator. And so in this case, we are still fine. Then also in this particular case, we only have double traces. The reason, again, is that the 3-point function, when we start considering this kind of operator, so this notation, maybe let me, these guys, this notation here means that those are M-trace operators, and we normalize it in this way. So you see that essentially triple trace operators starts appearing at order 1 over n to the 6. Okay, so this is 1 over n to the 4, so still we only have double trace operators, so we still have access, when we study G1 and G2, we have access to double trace operators, and if we start going to, for instance, G3, we are going to have in the OP decomposition both double traces and triple traces, and so on and so forth. So the more we add here terms, the more we can explore. So one way to study these Eiger trace operators, which now are mostly mentioned by Eiger trace triple trace operators. We have that we can either go in this direction, as I said, in such a way that by doing this partial weight decomposition or conformal block decomposition, we have access to this kind of operators here. So this is one way to go. Another way is, as I said, instead of studying 4-point function of single trace operators, we can go and take one of the external operators to be a double trace. So instead of studying O itself, we study the double trace of O. And then, for instance, if we take one double trace and 3 single trace, so each time that I put this dt means a double trace. In this particular case, the 3-point function of these guys is contains already a 1 over n. So in this particular case, already a leading order, which I mean at order 1 over n squared, so in the 3-level part, we are going to have a triple trace operator. So you see that we can either access triple trace by going here in this direction, so studying single trace but Eiger in loop, or we can start introducing Eiger trace operator, and by doing that we explore already Eiger trace at very leading order. This was just a way to tell you what could be the various options that you have to study such operators. So what I'm going to present today is this second scenario. Okay, so the aim, the final goal would be to use together this way together with this other way. So combine together the study of Eiger loop correction, so to large n correction of a 4-point function of single trace operator together with this double trace. But today I want to focus on this scenario 2. Okay, so let me just start by listing for you what is the sect, because, okay, so far this is fully generic. It doesn't really require to have n equal 4 super Yamils. I want it to be a bit more generic, but now I want to switch to n equal 4 super Yamils. So what is the main advantage of n equal 4 super Yamils? The main advantage, together with having this connection with amplitudes in ADS, there is also the fact that we have a set of operators which are protected operator, which essentially they are much more easier to deal with, because again they have the dimension which doesn't acquire any anomalous correction together with that 3-point function. So this is the main difference, and this is what we are going to use heavily. Let me list them a bit, and then we can discuss a bit more what they are. So generically, I'm going to discuss in this talk 2 classes of protected operators. So the first class that I'm going to discuss is half BPS operators. So the dimension of half BPS operator is fixed to be some number. And this number is essentially related to the way in which they transform under R symmetry. So if we take half BPS operator, the dimension is equal to P, and they transform under the 0P0 representation of SU4 R symmetry. And I wanted to mention that the 3-point function of 2 half BPS operator with another half BPS operator is just a function of n. So here I didn't put any lambda, not because it's a typo, it's just because this object, they just depend on the central charge, on the rank of the group, but they don't depend on the coupling constant. So this does not depend at all on lambda. Those are dual to states on the ADS, and the mass is related to this to the dimension here, and P is related to the angular momentum. So now we want to go back to the question before. So what are the single traces, what are the double traces? So up to P equal to 3, this half BPS operator, which here I wrote it, this is maybe is not 100% correct, it's just a symbolic way of writing it. So if you have O2 So this operator, which has dimension 2, is essentially trace of phi square. If you have p equal to 3, you have roughly trace of phi cube. So both of them, they are essentially dual. For instance, if you take this operator O2, this is dual to the graviton. So those are scalar operators on, sorry, there can be generic operator in the ADS. So in particular, this guy sits in the same supermultiplet of the graviton. This guy is a Kaluza-Klein mode of the graviton. And also, when you go to p equal to 4, you have actually two options. One option is to have this guy trace of phi to the 4, which again is similar to the guy that we said before. But now there can be another guy. So this operator here, which is trace phi square, trace phi square, you clearly see why you cannot have anything before dimension 4. And this is dual to a bound two-particle state on ADS. Okay, so already in the half BPF sector, we have two options when we take large enough dimension. So we have the possibility of having a single trace operator or an operator dual to a single particle state on ADS, but we can also have a two-particle state. And those are the guys that I'm going to consider. Okay, so then we also have another set of protected operators, which are a bit less protected than the half BPS one, which are quarter BPS. And here we have a bit more complicated representation of SU4. Those are also bound states they are dual to bound states in ADS, and I'm going to consider mostly these guys that they transform in the QPQ of SU4 symmetry, and the dimension again is fixed by supersymmetry to be of this number here. So now the issue with this quarter BPS states is that it is not 100% clear how the 3-point function of this operator is, so if it is protected or not. For some operators, we know that their 3-point function is protected, for other not, so generically I didn't want to write anything. The only thing that we are aware of is that this dimension is completely fixed. So let me just write down an example. So if we take this O02, this is going to be an object of this form. So you see that they are multi-trace by construction. So all quarter BPS operators are multi-trace. So they have essentially more or less the same structure as the previous guys. So there will be trace of phi I, phi j, then phi k, phi l, and then there is a projector here. And this projector essentially tells us which is the SU4 representation under which this operator transforms. Okay, so differently from the previous one, there is this object here, which makes it have a different way of transforming under that symmetry. Okay, sorry. And these guys, they have dimension 4, and they transform under this representation of R symmetry. So I'm going to present both cases. I'm going to present these correlators whose external operator involve this one here and the previous one that I showed you earlier. Okay, so this is what I just said. So I'm going to consider 4-point correlators made of single and double trace operators, both half BPS or quarter BPS. And what is the logic behind? So the logic behind is that essentially what I'm going to use heavily is the fact that now when we consider the operator product expansion of such operators, they can either be half BPS or quarter BPS, there will be inside this operator product expansion a certain sector of operators which is protected. And we would like to understand how to deal with this protected part. And then from this protected part, infer information about the anomalous dimension of double and higher trace operator, which instead depend on the coupling constant. This is just an overview. I'm going to be more specific later on what I mean. But this is the idea. So study 4-point correlators where we have double trace operators. Okay, so let's start with the simplest case, even if we did the opposite. So we started with, chronologically, we did first the quarter BPS and then the half BPS, but let me start with the half BPS. So let's consider 4-point function of 4 half BPS operator. So I already said how do they transform under R symmetry, and here I listed the dimension of those operators that we know they are protected from supersymmetry. And the way in which we can write this 4-point function using now superconformal symmetry is essentially we can write down a kinematical term here, and then we can write down this 4-point function. So this is nothing very special, but essentially now, since these operators they transform under some R symmetry, we need to take into account how they transform under this R symmetry. So we need to introduce some null vectors, which essentially denote the R symmetry. So essentially this we need to introduce, in addition to the usual cross ratios, also sigma and tau, which are called harmonic cross ratio. This is nothing very special. Now, what do we have? This correlator here, this function g curly g, contains information of all the primaries, as I said before. This is essentially the same as we had in the previous slide, that transform under the tensor product of these two representations and under these two. Essentially, here I'm just considering all the possible R symmetry representation under which the intermediate operator can transform. So now we didn't use as much as possible supersymmetry. What is very important is the fact that we can use the superconformal word identities. All this work started with some paper, I forgot to write it down. I think I had it, but then it disappeared, by Dolan and Osborne about a bit more than 10 years ago. And this, if we study the superconformal word identities, the solution to the superconformal word identity, we are able to disentangle the contribution of protected operator in this among all the possible operators that appear there. And so, for instance, if we consider the simplest possible single trace operator, there are several representations. And for instance, here you already notice, I just put a circle here just to let you notice that among all these operators, there will be some half BPS operators sitting here, but also in other representation. This is just an example. And then, by solving the superconformal word identities, we can write our 4-point function in this way. So we will have a part here, which essentially contains all the protected operators that appear inside this, the operator product expansion of my half BPS operator. So this function does not depend at all on lambda, while this function here instead takes into account the contribution of the long multiplet. So this function R is just, again, a function that is completely fixed, is kinematical. And then there is an information here of operator coming from long multiplet. Okay. And in addition, this function H now can be expanded in this way here. And now, instead of expanding this in a conformal block, we can expand it in superconformal block. And the main difference is that now, on this sum, it runs only over the dimension and the spin of the superconformal primaries. That's the most important point. And the R symmetry of the superconformal primary is restricted to be this one here. But the most important point that I want to convey with this is this part here. So if we are able to solve the superconformal word identity, we are able to essentially strip off the contribution of the protected operator which appear inside our operator product expansion. So now what is the strategy? So the strategy is that we start with our protected operator. Then we compute the protected part of the correlator by solving the superconformal word identity. And then we use crossing symmetry to see which consequences has in, so imagine we completely fix this function, then we say, okay, using crossing, what can we say about this function h? That's the logic. Let me just briefly mention how we do it in practice. So what's the tool that we are going to use? So the tool is the inversion formula. So the Lorentzian inversion formula put out in this paper in 2017. So essentially, the idea is that we would like to understand how to relate the operator product expansion with the correlator itself. So we can essentially study the singularities as v goes to 0, and then essentially relate this C, that I'm going to specify in a second what this is, with the double discontinuity of my correlator. So what is the double discontinuity? The double discontinuity is nothing but the difference between the Euclidean correlator with the analytic continuation around z bar going to 1, or essentially is equivalent to 2v going to 0. So what is the point? So the point is that now we are going to input here inside my correlator here, I'm going to study essentially the singularity of the protected part to get information about this C here. So what is C? This function, this object C has poles at the dimension of the exchange operators, and the residues is the square of the 3-point function. So the main logic is this one here. So we study the protected operators. So we fix the function of the protected operator. This function will have singularities, and we would like to understand how the singularities of this protected part is reflected into the non-protected operators. So that's the whole strategy. And actually, let me just go to this case here, where we have up VPS operator of dimension 4. So you see, this is what I just mentioned before. So at dimension 4, we have two operators. So we have one operator, which I denoted with SP, which means single particle. So you see that this is a linear combination of an object which is essentially a double trace, and an object which is a single trace, but this object is dual to a single particle state. And then there is another operator, which is actually genuinely dual to a multiparticle state that we denoted by dt. This is very nice that this actually happens for any p. So we studied the correlator of, okay, these two guys are orthogonal among themselves, and they actually, the 3-point function with all the single particle is 0, and with the double particle is different from 0. And then what we did, we used again supersymmetry, the same story that I told you before. So we studied this correlator here, where two operators are single trace and two of them are double trace. We computed the protected part, which looks like that. So here you see just n squared minus 1, because this is the central charge of the theory. So this we completely fixed. Again, I put a double trace just to remind ourselves. So what we found, this is not very special, but the intermediate operators that we are going to have in this case, they are all SU4 singlet. We computed the anomalous dimension and the correction to the OP coefficient of double trace and triple trace operators appearing in the OP. In particular, at twist 6, there are triple trace operators, as I mentioned before. The results are very long, so I didn't put it here because I don't think it makes much sense to show them to you, but there are explicit results for several twists. Then is some issues with mixing, meaning that there is more than one state which has the same quantum number, but at low enough twist, there is only one operator, in particular in the triple trace sector. Let me just, sorry, this is very important. Our results agree with the supergravity-based one that have been found in this paper here recently. Actually, by looking at the web page, I saw that Rodolfo gave a talk in the last year, Eurostrings, about something related to that. So maybe for those of you who attended the last year, you can see the differences. Let me just quickly flash what happens for double traces. So what we did for double trace quarter BPS, we essentially studied this kind of correlators, for instance, 3 half BPS operators, single trace, and 1 quarter BPS. And actually, we show that this is protected, meaning that this does not depend on the coupling constant at all. Then we studied these correlators here, so 2 half BPS single trace and 2 double trace and 4 double traces. We reconstructed completely the protected part up to 1 over n square. But now there are some difficulties that I would like to mention before ending, is that first of all, there is a proliferation of arc-symmetry structure. For instance, in this O2 times O02, there are 10 arc-symmetry structure, and here there are 42. But the main problem is the fact that the solution to the superconformal word identity is not known, meaning that essentially the form of superconformal block is not known. So we just worked at the level of conformal primary, which is much less powerful. Luckily, a month back, there was this paper here that we are trying to understand. This is like a lot of super space, so it requires a bit of time to digest. But it seems that now it is possible to study superconformal block also for quarter BPS operator. Also for this case, we computed the anomalous dimension and the OP coefficient of some classes of operators. Again, in this particular case, those are conformal primaries, up to twist 6. Let me just conclude, because I think I'm out of time. But okay, what I wanted to show you today is essentially that we have some hope to be able to understand higher trace operators, so essentially to include in our study of the spectrum of n equal 4 even higher trace operators. So for double trace operator, a lot of information are known. For instance, we know that the dimension of double trace operators, for instance, for large spin goes in this particular way. So where this tau min is essentially the operator which has the smallest twist in the spectrum, but we don't know anything of this form for higher trace operator. So this is actually what we would like to understand, try to understand if there is any way in which we are able to completely systematically understand the spectrum of higher trace. And in order to do that, we need to understand the superconformal block for quarter BPS operators. And what we are currently trying to understand is what happens when we include all this information together. So when we put all this information together, you remember there was scenario 1, 2, 3, and so on. So we are trying to understand, for instance, what happens when we put scenario 1 and scenario 2 together, and what we are able to say again about this object here. Notice that before I just glissed around the fact that there is this degeneracy and so on. So technically this is a bit complicated to solve. And actually, if you put together all these correlators, so you study a kind of system of correlators, it's easier to solve this mixing and these degeneracies. So this is what we are currently trying to understand, and also together with this other thing of understanding the superconformal block. But this is all I wanted to say, so thank you very much.
Thank you. Question from
Hi, so I want to ask you, can you get information about the matrix elements of the non-planar dilatation operator between a single trace and double trace using these techniques?
Yeah, so essentially, in order to construct our states, we used that object, because in order to define what is an operator, we had to do that. So when we talk about operator, we mean the eigenfunction of the dilation operator. That's the reason why I was writing these two operators with this n. But this is essentially what we did in order to define what is an operator. We just diagonalize essentially the dilation operator. I understand what you maybe wanted to hint to, like just use more the matrix that we have, but we didn't do that.
Yeah. Can I?
Thanks for the nice talk. I want to ask that if I want to consider the setting like with the 1/2 bps Wilson line inserted into the equals to for supermills, and I want to use this technique in your talk to study the, let's say, single trace and double trace or multi-trace operators on the defect. Do you think like I think that the technique shall apply, but can you like think of more difficulties in the defect case, or you think it's easier?
I think it's more difficult. The reason why it's more difficult, more difficult is because I know how to do this, so I think this is more difficult. But it should work. The issue with that is that you have less symmetry. So each time that you insert a defect, you reduce your symmetry. Yes. So by reducing your symmetry, the symmetry constraints are a bit less powerful. So I'm not 100% sure if you are able to work out exactly the same steps we did because of this reason, because you have less symmetry. So you are breaking your symmetry by including a defect. So for instance, you already have a 1-point function which is not 0, or you start having 2-point function that will still have some kind of constraints. So, but I think it is possible. It's just that technically, I think it's a bit less known on how to deal with it.
Yeah, I see. Thank you.
Yeah, sorry. Sorry, I'm a bit ignorant about the superconformal block issue. So what do we know about them? We know them in terms of series, and you would like to have a more closed form expression?
We know what their definition, but we don't know their form.
At all? We don't know.
We know for 1/2 BPS, for instance, if you start with 2 1/2 BPS, with 1/4 BPS, we don't know them at all. As far as I know, in this paper that I mentioned, there is some kind of, in principle, you can just build the super Casimir operator and find eigenfunctions. Yeah. But this is a complicated differential equation, because now it's not like having a 1/2 BPS operator, you have 1/4 BPS operator, the symmetry is a bit less, so you start having many more variables which appear, so it's more complicated. I'm not saying that it's impossible, it's just more complicated. We tried for a few months, but then we said, okay, let's... Sure, thank you.